Welcome to our first video presentation for Unit 8, Electrics, and this to my mind is certainly the most important unit that you'll actually deal with this year. There's a few reasons for this. Part of that is shown in the graph you can see here. The sheer cost of electrics as a makeup of the overall price of a car has shot up. 1950s, 1% of the cost. Up to 1980, where it represented 10% of the cost. These days, up all the way up at 2020, the actual electrics is 35% of the actual cost of the car. Now that is not for an electric vehicle, that is an internal combustion engine vehicle. And we can see within the next 10 years, they're expecting that to shoot up again, up to 50% of the total cost of the car. Now, with all this investment in electrics and electronics on the car, there's an awful lot more in that area to go wrong, and it does. It's really, really important for you to have a good grasp, a good understanding of the electrical system and the electronic system if you're going to work with these systems and diagnose them successfully in your career as a motor mechanic. A good understanding of these systems is effectively your roadmap to able to repair them. If you don't understand them, well, it'll be a bit like trying to take your car from Jersey to Rome, driving without even knowing how to drive. A good diagnostic technician uses his knowledge of the systems along with the tools such as fault code readers, such as voltmeters, such as oscilloscopes, to help diagnose any problem that he comes across on a car. But you can bet that's all based on having a really good grounding on how these systems work. And that's what we're going to try and achieve here. So as far as the actual unit itself is concerned, as always, Learning Outcome 1 is going to be done by a test. Learning Outcome 2, you're going to make and test a couple of different electrical circuits. And Learning Outcome 3 is going to be reviewing your findings based on the tests that you conducted on those circuits. If you're watching this as part of our remote lesson, then please do go onto Teams and download the worksheets that accompany this so as you can actually take part in the lesson as we go. So without further ado, let's crack on. So my first question to you is, what is electricity? Have a think about that. What actually is electricity? And what I'd like you to do now is pause the video, go back onto Teams and post your answers on the team chat. Okay, thank you for that. So the answer I'm going to give you, the model answer, is that electricity is a type of energy that can either build up in one place or it can flow from one place to another. When electricity builds up in one place, that is known as static electricity. And you've probably experienced static electricity if you've ever rubbed your feet on a nylon carpet then touched something metal. That crack, that little sharp pain that you get in your hand, that's an example of the static electricity flowing to earth. It's actually started moving again. So as you're rubbing your feet on the carpet, your body actually gradually builds up an electric charge, which can be felt sometimes as a bit of a tingling. When you touch the metal, the charge runs instantly to earth, and that's that shock that you feel. Electricity that moves from one place to another is called current electricity. And this is the type of electricity that we're really interested in when we're dealing with cars. In current electricity, electrons move and carry electrical energy from one place to another. And in current electricity, we get both AC and DC, which stands for alternating current and direct current. Now, alternating current, an example of that might be the light bulb in your house, whereas direct current is the battery in your phone. And what we're going to do next is have a look at what are electrons. And for that, we're going to have a bit of a closer look at atoms. In the classic view of an atom, you get often images like this, of a nucleus in the middle that's got neutrally charged neutrons and positively charged protons. then orbiting around the nucleus, you've actually got negatively charged electrons, almost like planets orbiting the sun. What I'd like you to do now is pause the video and complete the actual gapped handout in your worksheets. So we've said in current electricity that the electrons are flying from one place to another. But the question is, why do those electrons move? What makes them want to go from one place to another? Well, to help with the understanding of that, we need to introduce some new terms. Those new terms are insulators, conductors, and EMF. As far as a definition for these, a conductor, in a conductor, the electrical current can flow freely. But in an insulator, the electrical current does not flow freely at all. The electrons are tightly bound to their atoms. So just for a moment, pause the video and have a look at the materials that are shown on the diagram on this page. Which of those is a good conductor? Well, if you've been paying attention, you will actually have correctly spotted that actually none of these are good conductors. They are all insulators. And what I'd like you to do now is pause the video and go back to your worksheets and write a description for the following two terms, insulators and conductors. Feel free to use Google for this to research it a bit more, or you can go back and have another look at the description I gave you in the video. However, what I would like you to do as much as possible is do put this into your own words, as it will help your understanding. So the third term, the one we haven't dealt with yet, is electromotive force. And we can actually think of that as the battery. To all intents and purposes, that's what's providing the electromotive force. Electromotive force is the push, the thing that's shoving the electrons around the circuit to provide that electromotive force. Okay. When there's no circuit made, we do have a potential difference. We've got electrons on one side of the battery that really want to get to the other, but there's no way for them to do that. Once we actually make the circuit, by closing a switch as an example, turning something on, then the electrons will flow under the pressure supplied by the battery. And what I'd like you to do now is pause for a moment and give me 5 examples on your worksheets of good conductors. So hopefully you didn't have any problems at all with that. And metals like steel, copper, gold, anything like that are going to be good conductors. And a conductor just means that those outer electrons of the atoms are loosely bound. They're not held tightly to the nucleus, and they can move freely through the material. What I'd like you to do now is, again, pause the video, go back to your worksheets and give 5 examples of good insulators. In this case, materials like plastics, wood, rubber, glass, they're all good insulators. They hold on to the electrons. They don't want them to flow through the material anywhere near as easily. In automotive wiring, the most commonly used material is copper stranded wire. Now, the reason we use that is, although it's not the very best conductor, it is a very good conductor. And the electrons are essentially free, but they do remember they strongly repel each other, and that's an important concept. Now, the fact that they strongly repel each other does mean that each atom can only hold on to so many. So when we actually connect our circuit up, we turn the switch to on, and electrons start flowing from the battery to try and get to the other side of the battery. The repulsion causes electrons to jump from one atom to the next. You can think of it a bit like a Newton's cradle, where we drop the ball, then it can only keep 4 on at any one time. We drop one onto it, the other one bounces off, and that goes on to if that was an electron, it would be going on to the next atom. Another way of looking at this would be if we had a pipe that's filled with marbles. If we try to push one more marble into the pipe, one's going to fall out the end. That's exactly the same with electrons. As we push one into the end of the wire, one has to come out the other end. So now we've had a look at what electrons are and how we get electrons moving. Let's have a look and see what we can do with them. Let's have a look at the effects of electricity. So the three effects that we actually can get out of our electricity are a heating effect, a magnetic effect, and a chemical effect. And what I'd like you to do now is pause the worksheet and see whether you can come up with automotive examples of each effect. Do feel free to use Google or have a look at one of the workbooks that we've got uploaded on Teams. So as far as our heating effect is concerned, you could look at the filament of a light bulb. The magnetic effect, well, that's what we use, that principle, in a motor. And the chemical effect is what we see both when we discharge and when we charge a car battery. What we're going to do now is we're going to have a look at circuits. We're going to move on to circuits. We're going to have a look at what we mean by a circuit and try and give you, we're going to look at a few more terms and try and give you some idea of how to transfer those terms into a form that you might understand a little easier than if we're just talking about something like an electron that you can't see. So the first thing is what we're talking about when we talk about an electrical circuit. We're talking about an uninterrupted path for our electrons to flow through, and it's going to be all the way from one side of our power source to the other. So by that, what we mean is the path has a complete loop all the way around. Now it's going to go through a consumer, and the cartoon on the page here shows you going through a light bulb. It's going to go through that. It's got to attach to both sides of the battery so the electrons can actually flow through. They're not going to want to jump across air. Air is a good insulator. So that circuit has to be a closed circuit. And the electrons are going to flow around that circuit, pushed by the electromotive force supplied by the battery. The next thing we're going to do is introduce three new terms, and those are volts, amps, and ohms. And the way I generally like to do this is actually use a water analogy. And so we've got this image here, this cartoon image here, which I think is absolutely fantastic, really explains it well. And that we can imagine that our electrical current is like water flowing through a pipe. We've also got our pump house, that's our battery, providing our potential difference, providing our electromotive force. We have the water pipes, those are our wires. And the gravel-filled pipe that you see at the front there, that's our bulb filament. Yeah, it's an electrical consumer, something that's going to take that pressure and make use of it. Pressure from the pump, from the pump house, pushes the water around the circuit. That's the same as the battery pushing the electrons around the circuit. Now, if this was a water circuit, we'd be measuring the pressure of the water in bar or pounds per square inch, depending what you wanted to. But in terms of electrical pressure, what we measure that in is volts. Volts is our electrical pressure. It's fairly easy to see that our gravel-filled pipe at the front there is going to resist the flow of water around the circuit. And in electrical terms, a resistance to the flow of electrons is measured in ohms. If we wanted to measure how much water is flowing through the pipe at any one time, we'd probably measure that in litres per minute. But in electronic terms or electrical terms, the flow of electrons is actually a measurement that we use as amps for that. So what I'd like you to do now is pause the video, go to your worksheets and complete the table that's at the bottom of the image. You can compare your answers here. Now, there are two different types of circuit that I want you to be familiar with. First one is called a series circuit. Second one is a parallel circuit. We'll look at the series one first. So what we've got here is a pictorial and a schematic diagram of the same circuit. These are both examples of series circuits, and we call this a series circuit is because one thing comes after the other. Okay, so in this case we've got a battery at the top, when we've got two light bulbs at the bottom. On the right hand side, in the actual symbol method or the schematic method, you can see the symbol for the battery at the top there and the two light bulbs at the bottom, the circles with crosses in. As I say, series circuit, one thing comes after the other. Think very much like a TV series. You have to watch one, then the next as it goes on. This is our second example of a circuit, and this is our parallel circuit. Again, we've got the pictorial on the left, we've got the schematic on the right hand side, and we can still see the same components. We've got the battery and we've got the two bulbs, but the way they're connected up here is very, very differently. So in this particular instance, each side of the bulb sees our battery voltage at its full rate. Unlike on the series circuit where it's split between the two bulbs, each bulb will see full battery voltage. Now, in terms of a car wiring diagram, that means we're going to be talking about a 12 volt voltage pressure acting on each bulb. Flipping back quickly to the series circuit, you can actually see that in this case, only one bulb actually sees the full 12 volts, and actually, if we measured across the bulb, we'd see it didn't. The voltage has to get split between the two. And again, if we were dealing with an automotive 12 volt battery, we'd actually see that in this case, each bulb only sees 6 volts. They share the voltage out. So most of the circuits that you're going to come across on a car are actually parallel. This allows each component to have its full 12 volt, and automotive bulbs are designed around a 12 volt system on the whole. There were a few outliers, but nothing around at the moment is actually going to use anything other than 12 volt. I am of course talking about the lighting circuit here of a normal standard bulb. If we talk about the hybrid electric side, we get a lot more than 12 volts. So we can represent our wiring, or our circuit I should say, in a diagram as shown here, a picture. We've got a picture of a battery, we've got a picture of a bulb, and we've got a line drawing representing a wire. But if you go into the workshop manual for most vehicles, what you're going to see is a schematic diagram similar to this, where symbols represent the individual components, and you've got to know what those components mean, or what they are, to be able to read the diagram. And the ability to read that diagram is massively important if you're going to have any chance at diagnosing problems with an electrical circuit. So because of this, the next thing I want you to do is pause this video for a bit and just go and draw a couple of circuits in your workbook. The first one being a series schematic circuit, and you've got the actual symbols on your worksheet, but I want you to include a battery. I want you to include 4 bulbs mounted in series, remember, one after the other. I want you to include the symbol for a fuse and a switch, and it's got to be connected in such a way that your circuit would work. Okay? Pause it now and go and do that. Right, the second circuit I want you to do is a parallel schematic circuit. Same thing, same components. I want you to include a battery. I want you to include 4 light bulbs, a fuse and a switch connected up in such a way that it would work, and also connected in a parallel manner. Again, using the symbols that are shown on your worksheets. All done? Great. Okay, our next step is what I want you to do is actually pause the video again and go and have a look at this video clip. Now you've got a link to it in your worksheet, so you shouldn't have any problems. You haven't got to copy this out by hand. What I want you to do is pay attention to what's happening to the light bulbs in the two different types of circuit. What's happening in a series circuit, what's happening in a parallel circuit. And also notice what happens when a fault is introduced on the series and a fault is introduced on the parallel circuit. I've also included another couple of links here. One is to the Autodesk.com site, and that actually goes through series and parallel very, very well. There's also a link to this YouTube clip, the second one shown on the page here, which gives you a little bit more information about series and parallel circuits. So to work out what's happening in these two types of circuit, we're now going to take a look at Ohm's Law and Watt's Law, also known as the power equation, and that's going to be the subject of our next video. So that's the end of this video, and my intention was for you to have learned the meaning of electrons, EMF, insulators, conductors, volts, amps, ohms, and circuits, both series and parallel circuits. What I'd like you to do now is make sure that you've completed all of the actual work within the worksheets and email that to me so it can be marked. Thanks very much. I'll see you in the next video.